Hi everyone. So for this advanced concepts presentation number 2 by me, Amanda Flores. So to start off for this presentation, we were asked to walk with the audience through the derivation process for the Michaelis-Menten equation. So we were given the equation below, which is E plus S, forward and backward reactions, to ES, forward reaction, to E plus P. So normally this would be the first equation and this would be the second. So this top one would be labeled K1, which is a forward reaction. This one would be K2, which is a backwards reaction. K negative 1. And then this one would be a forward K2 reaction. So here, the enzyme and the substrate reacting together form the enzyme-substrate complex, which is also known as the Michaelis-Menten equation. So from this equation that we were given, we can get the instantaneous rate of change, which is d of ES over d of T. So we're going to use K1, reaction of K1 times E times S minus K negative 1 of E of S minus K2 of E of S. So all this comes from the equation up above that was given. And once we've created this equation for the instantaneous rate of change, we are going to set it equal to 0. So this expression right here is going to express our mirrored method for initial rates, which depends on the concentration of reactants. So then, separate this. We have E sub T, which is the enzyme total, or total enzymes, times is going to equal E plus E of S. So then moving it around to solve for E, you're going to get E is equal to E sub T minus E of S. So with this equation, we're going to plug it in to the E in this equation. So doing that, we're going to get d of E of S over d of T, which is going to equal K1 times this, because remember we're substituting it for E, so it's going to be E sub T minus E of S times S. And then we're going to subtract K negative 1 of E of S minus K2 E of S. So once we have this reaction of the instantaneous rate of change, we are going to set it equal to 0. So once we do that, we are going to move, well, more like organize our equation. So by organizing it, we are going to do this. So we're gonna have 0 is equal to reaction of K1 of E plus of E of T times S minus K1 times of minus K negative 1 of E of S minus K2 times E of S. So once we have that, we're going to organize it by kind of putting ES to one side and simplifying it more further. So we're going to put E of S times K1 times S plus K2 negative 1 plus K2, which is going to equal to K1 times E of T times S. So we're going to simplify it even further. So then it becomes E of S is equal to K1 E of T times S over K1 times S plus K1 plus K2. Okay, so now simplifying it even further, we get E of S is equal to E sub T times S over S plus K negative 1 plus K2 all over K1. So then getting the instantaneous rate of change, we're gonna get D of P over D of T, and this P was found in the first equation. Where is it? In the given, which is equal to K2 times E of S. So now that we have this equation, we know that the velocity, we're going to go up here, that the velocity is equal to this. And this equation is going to be equal to E sub T over S and Km. So going further, this is transformed to Vmax, but I can't really remember how Vmax is obtained. So V is equal to Vmax times S over S plus Km. So once we get this equation, which is the Michaelis-Menten equation, we can simplify this one to be able to kind of find more reactions easily. So we were also asked to define Vmax. So as the enzyme substrate goes up, the rate of reaction also increases, which is important to keep in mind. So if E of S, which is the enzyme substrate, is equal to the enzyme total, meaning that all the enzyme substrate is saturated with the substrate. So let's say E of S is equal to E of sub T. If these are equal, that means that the enzyme is saturated with substrate, so that the reaction is at its maximum. The reaction rate or the velocity, which is what Vmax is. So Vmax is the maximum reaction rate or velocity. So we were also asked to define what Km is. So Km is the Michaelis-Menten constant. And that constant is equal to K minus 1 plus K2 all over K1. And Km is the concentration of substrates where the reaction rate is half the velocity. So Km is where the reaction rate is half of the initial velocity. So just also to know, when Km is high, you have a low affinity, and when Km is low, you have a high affinity. So when it is graphed, I apologize for this very ugly graph, and it would be something sort of like that. The Vmax would be up here. Your half of velocity would be somewhere around here. And your Km would be right here. So this is my presentation for Advanced Concepts number 2, and I hope I did well. I was a bit confused, but this is it. So thank you.